Welcome to Lesson 64, Algebra 2 students. You have made it to the last lesson of the first semester. I am so excited. So, we are going to do something that's not quite so hard. It's called complex fractions and complex numbers. And the truth of the matter is, you guys have already been doing these. And there we go. It was disconnected for just a second. Any fraction that contains more than one fraction line, we call it a complex fraction, right? So it's a complex fraction if it looks anything like this, where you have 1b plus x over some other fraction, right? We've got a couple of different fractions being divided and being turned into fractions themselves. So that is what we consider a complex fraction, but we can simplify this. We just keep it, change it, flip it. First, we get some common denominators going up here. Okay, so this would end up being, we need a common denominator of b, so we multiply this by b, so it'd be 1 plus xb over b, right? Keep it, change it, flip it means we change the sign and flip, cancel, and we have 1 plus xb over a. That would be our result. All right, so we can simplify complex fractions. And the point of simplifying this is to put it in something like this. We want to take it out of a complex form and into a simplified single fraction form. That's what we've been doing for a while now. And y'all have gotten to be pretty good at it. But that's what we're going to be talking about, just a little bit more, just slightly more complex than this. So let's look at 64.1. And in 64.1, we have this. We have a plus 1 over 1b plus x. All right, so that's fairly complicated. So we begin by simplifying this right here. Right? So we turn this into a plus 1 over 1 plus bx over, what did I write? I'm losing my mind. 1 plus bx over b. So now we have a single fraction here. And we're going to multiply that. We're going to keep it, change it, flip it, and multiply that. We're going to do that over here to the side just so we can keep track of it. So 1 times b over, and that's 1 over 1 times b over 1 plus bx, right? So 1 times this and 1 times this equals this, right? So what we end up with is a plus b over 1 plus bx, right? Because we simplified it here. So we got this canceled out and we just had this. So we put this right here. We simplified all of this into this. Now we're going to simplify and make this have a common denominator. And the common denominator is going to be 1 plus bx. All right, since this is over 1, we multiply this whole thing by 1 plus bx. So we get a times 1 plus bx plus b all over 1 plus bx. Easy peasy. That's the answer. All right. Pretty straightforward. We have one more to do like that. It's just adding another element to our already complex fraction. So 64.2 is another one like that. We have a over x plus 4 over 1 plus, why do I keep making a plus sign out of the number 1? Something is wrong with my brain. All right, 1 plus b over x. All right, this is the problem. So first we go to our most specific term, which is going to be this underneath this fraction. And we're going to turn this into a single fraction here. So we'll do that over here on the side. We'll just say that we need to multiply this by x. So that's going to be x over x plus b over x, which is going to equal x plus b over x. All right, so we would replace that and say a over x plus 4 over x plus b over x. So then we would get rid of that by doing a little keep it, change it, flip it. So we would keep the first and we turn into a fraction, change the sign, and flip, right? And that's one of the reasons why I like to use a dot once we get into higher math, because the x's run together. You don't know if it's multiplication or what it is. So let's flip this second one, and we put x plus b on the bottom, right? So that's going to equal 4x over x plus b. So now we can bring this in here and rewrite this. A over x plus 4x over x plus b. Now we're going to make this have a common denominator, and that common denominator is going to be x times x plus b, right? So we'll go ahead and write our fraction here, x times x plus b, right? And then we're going to multiply. Now this one has to be multiplied by the opposite denominator, just like in our regular math. We just do the opposite denominator. So this is going to be a times x plus b, right? And when we say x times 4x, we get 4x squared. That's it, ladies and gentlemen. That's our answer. Now, if you want to, you can take it out further and say ax plus ab plus 4x squared, and put that over x squared plus bx. It's the same thing. Why take the extra step? If this is correct, it's entirely up to you. But leave it like this, it'll be marked right. And you don't have to try to do extra distribution when it's not necessary. All right, so that is all we had for the first part of lesson 64. Now we're going to talk about complex numbers. So complex numbers, we remember that we say that any number that can be graphed on a number line is a real number, right? So here we have a line. And we have some pretty weird numbers on this line. We have, let's see, -1, -2, -3, -4. And over here we have 1, 2, 3, 4. Right on this side we have, right about here, we have -2 times the square root of 2. And then over here, we have a +2 times the square root of 2. So both of these numbers are real numbers. Square roots of negative numbers, or numbers that have I as a factor, cannot be graphed on the number line. So if it were to have this inside, we can't put it on the number line. But as long as this is positive underneath this radical sign, it can go on the number line, okay? So we call these numbers that can't be graphed, that have this designation here of a negative under the radical, we call them imaginary numbers. And because they're imaginary numbers, they are not real numbers. So we call it a complex number. Something like this would be considered, we could turn this into the square root of 2 times I. That would be a complex number. And if the real part is written first, the imaginary part is written second, like we did here, we say that the complex number is written in standard form. We define standard form to be the form a plus b with the imaginary part second, where both a and b are real numbers. Since 0 is a real number, then 0 plus 2i is 2i. And 7 minus 0i is 7. and they're complex numbers written in the standard form. Thus, every real number is a complex number whose imaginary part is 0. And every imaginary number is a complex number whose real part is 0. That makes sense? Okay, never mind. For this reason, we say that all of the following real numbers and imaginary numbers are also complex. So this would be a complex number. 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 And this would be a complex number. So everything is a complex number. Some of them have imaginary parts and some of them don't. So I'm not sure why the lesson decided to go in that direction. If it were up to me, I probably would have stopped right about here and not gone any further. But I am not the designer of the lesson. So let's move on to solving some problems using this information that we now have. If we want to simplify -2 times -3, both of them squared, we remember that when both radicands are negative, the radicands cannot be multiplied to change the form of the expression. First, we must use Euler's notation. Remember? Euler's notation is the square root of -1 times 2 times the square root of -1 times 3, where these are both I, right? So that would be the square root of 2 times I times the square root of 3 times I. So what we end up with is the square root of 6 times I squared. But I squared equals -1. So instead what we would do is say negative square root of 6. Because the square root of -1 and the square root of -1 is going to pop out as a -1. And the 1 is always invisible. But this is literally what we're doing when we write this. It's the same thing as this. We just don't need the 1 to remind us. What happens when mathematicians write things down is they want to make the least number of marks possible. And if you have a bunch of 1s in place, sometimes that can get confusing, especially if you're doing a bunch of negatives and 1s together. That can start to look like a cross, right? Or like a plus sign. So it could actually alter their calculations. So they leave out 1s on purpose for the sake of simplification. Okay. All right, so now we have another one, 64.4. That one was pretty straightforward and easy. We're going to simplify 4i cubed minus 2i to the 4th plus 2 times the square root of -9 plus the square root of -3 times the square root of -3. All right, so first we use 3 steps. The first step, we're going to simplify these i's. So let's do that. So we have 4 and we have 3 i's. So we're going to put 2 of these i's together and leave 1 by itself. Same thing here. We have 4 i's, so we're going to do I squared and I squared. And then over here, we're going to say 2 times 9i plus the square root of 3i times the square root of 3i, right? Now let's go back to the beginning. And let's look at what we have. Now we remember that a I squared, that's going to be a -1. So this becomes a -4i. This becomes -1 times -1, which is a +1. They cancel each other out. So this remains a -2. plus 2 times 9i. We can't really do anything with that. Actually, I take that back. We can pull 3 times 3 out of here, and 3 times 2 is 6, right? So we could actually pull out and say 6i here from here. And then for here, we have square root of 3 times the square root of 3. Well, that's going to be 3. And then I times I, that's negative 1. So that would become a negative 3, because 3 times negative 1 is a negative 3. So now we can combine, and we can say negative 4i and a positive 6i. It's going to be a 2i minus 5. And that would be our resulting answer. All right. We see how we can kind of get around some of that. We took all of this and turned it into this and simplified. Let's do that a couple more times. Let's clear the page, and let's do 64.5 right here. And we have 4 plus 2i times 3 minus 2i. All right, we treat this just like any other variable. That's going to be 12. And then that's going to be negative 8i. And this is going to be a positive 6i. And that is going to be a negative 4i squared, because we have 2 i's here. So now we can reduce. We have 12. That's going to be minus 2i. And then this is going to be a negative 1. So negative 1 times negative 4 is a positive 4. All right. Yes. And that is, we can then combine these two, because that becomes a number, a whole number now without the variable I. So then that becomes 16 minus 2i. And that is our final answer. So 64.6. This is our final problem. We have 5i minus 2 times 4 plus 3i. So I want you to pause the video and work this problem. Come back and check your answer. All right, if you got 14i minus 23 or negative 23 plus 14i, then you got the correct answer. And the way we did that was we multiplied 5i times 4 and then times positive 3i. We got 20i and 15i squared. And then we multiplied negative 2 times 4 and positive 3i, and we got negative 8 and negative 6i. We were able to combine negative 6 and positive 20i into a positive 14i, and positive 15 times negative 1 is a negative 15. And then we were able to combine that with the negative 8 to get a negative 23. So 14i minus 23 is where we landed. And that is all we have for lesson 64, the last problem of the last lesson of the first semester. I hope you guys have a really, really great Christmas break. I will see you in a month. That's a long time. I'm going to miss you very much. And you will have homework before the first day of school. So anyway, I just wanted to say I'll see you Thursday. Ta-ta for now.